Okay, now we're going to lesson 3 of the series Demystifying Compilers, and we're talking about the Syntactic Analyzer. Let's recapitulate. 2 lessons ago we saw a general overview of the whole process of compilation. We saw that it is formed by a lexical analysis, that was the subject of our last lesson, where the individual words and symbols of the code, the lexemes, are mapped into tokens kept on a symbol table, and it is checked if either or not all of them are valid. A syntactic analysis, that also called parsing, where it is checked whether or not the sequence of tokens is correct. A semantic analysis, where beyond other issues, it is checked whether or not there is a consistency on the usage of type declarations and type expressions, and at last a code generation and optimization phase. So this is the overall process we saw on the last 2 lessons. From the program code we have a sequence of steps in order to reach the machine code that goes from lexical analysis, syntactic analysis, semantic analysis, and code generation and optimization. On this lesson we will focus our lens on learning some concepts that will allow us to specify syntactic analyzers. So come with me and I'll teach you everything I know. So in order to check if a given sequence stream of word symbols is correct, if they correspond to a compilable program, we must at first determine a model to represent all possible codes that can be written for a programming language. But as there are infinite possible programs for a programming language, how to describe these infinite manners in a finite manner? For that we make use of grammars. Given a code of a program as an input stream, a grammar is a model that has a set of formal rules that successfully apply to the token stream of that code, determine if it belongs or not to the programming language that is described by the grammar. If there is a sequence of rule applications, also called derivations, that reach that token stream, or if the token stream can be transformed or synthesized to the root of the grammar, then it belongs to the language described by that grammar. Grammars are formed by productions that are formal rules with the following symbols: non-terminal symbols, terminal symbols, and lambda symbols. On the family of grammars that we will consider on this lesson, context-free grammars, there is always a non-terminal symbol on the left side of a rule, and a sequence of one or more symbols, either terminal or non-terminal, on the right side of the rule. So we have an input token stream and a grammar, and we want to answer the following question: does the token stream belong to the programming language that is described by the grammar? And there are 2 manners to check that. We get the grammar, we consider the grammar, and we try to derive it to the input token stream. In the other manner, we have the input token stream and we try to synthesize it to the root of the grammar. So these are both forms. One is called top-down and the other one is bottom-up. So consider a grammar of a language LP that accepts a number of 1 or more A's or B's and mandatorily ends with an A as follows. So we have this grammar. On the grammar above, P is the non-terminal and also the root, and A and B are the terminals. Suppose that we want to check if sequence AB, AB, AB is accepted by the grammar. So let's try to derive this on the previous grammar. So we make a series of derivations, and then we reach this state here: AB, 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 and then the non-terminal P. So we should either be able to generate an NDB after AB, AB, AP, or an empty token after AB, 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 P, but neither of them is possible. So this is not a possible code for language P. Now let's rescue that exercise we did in the previous lesson. We considered a subset of Java with respect only to type declaration, and asked that the use types were int, float, double, and string. One of the possible examples of program for the subset of Java that we described so we have this program: float x equals 0.1, int y equals 0, int z, string str, str2, and str2 equals dashes. But how do we make a grammar for the subset of Java we considered? Let's reason about this on the next slide. So for making a grammar for a programming language, we must at first reason about what are its major blocks. In our case, we know that our program is simply formed by a sequence of variable declarations like this, And as we must have at least one variable declaration and a semicolon, var declarations could be like this. So each variable declaration of the sequence can be formed by one or more names, list of declarations of variables, like in string str, str2 equals dashes, preceded by a type name. So update vard on production vard cls, we would reach vard cls going to either type declist semicolon vard cls or to only type declist semicolon. So we do this process until we reach all the tokens of the programming language. We see the complete grammar of our subset of Java on the next slide. So we have here the complete grammar. The root is program, then we go to non-terminal var dcls, and then you can go either to type declist semicolon var dcls or to type declist semicolon, and from var dcls, from type we can go to int float double string. From declist we can go to id asgn colon declist, and so on. So let's check if the following token stream is accepted by the grammar on the left. So it's the program we had previously, and let's try to derive the grammar from its root to this program. So there is a series of derivations here, and after many derivations we see that we in fact can derive, from the root of the tree of the grammar, we can reach the token string. So this is a top-down process, as we will see on this slide, because we check that the token stream is accepted by the grammar by trying to derive it from the initial non-terminal program towards its terminals. There are the tokens on the grammar without changing the input token stream. So we get we go from the root downwards the token stream. There is another process in which we start from the token stream, and then we try to synthesize it to the program, to the root. And this process is called bottom-up. So on this lesson we learn how to build a grammar for a programming language and how to check if a given code, that is the input token stream, belongs to the programming language described by the grammar. On the next lesson we will deepen on algorithms of syntactic analysis and investigate some issues related to the construction of grammars that can be read by such algorithms. A huge thank you from the computer scientist. Subscribe on this channel, like this video, push the little bell such that you receive notifications for my new videos, and make questions and suggestions on the comments. Tell me your thoughts about this lesson and the previous ones. I want to hear you. With your feedback, you'll help me to give you an even better content.